we want to begin looking now at another classification of functions called rational functions. And the word rational should remind you of fraction, because a rational number is of the form integer divided by integer as long as the bottom integer isn't 0. That's the definition of a rational number. So a rational function is the same idea. It's a function divided by a function in which the two functions are polynomial functions and the denominator is not 0. So for example, if I take a polynomial function, and remember a polynomial function is one in which we add or subtract terms with variables that have whole number exponents, 3, 2, 1, 0, etc. There's a polynomial function. And if I divide by another polynomial function, I get what I call a rational function. And this is my rational function as long as the denominator is not 0, which is in this case 4. And as we're going to talk about, the fact that rational functions have non-permissible values makes their graphs and the graphing of them more complex. Here's another rational function, x minus 3 polynomial divided by x plus 2 polynomial. As long as the denominator is not 0, we have a non-permissible value at negative 2. Here are two functions which are not rational. This one is not because our numerator is not a polynomial function. And remember, it's not a polynomial because we have x to the 1/2. We have an exponent which is not a whole number. It's a rational number. It's a fraction. Can't have that. All right? So this is a function, but it's not a rational function. Okay? And this one certainly is not because we have the variable in the exponent, and that's not the form of a polynomial. This is an exponential function, so it's not rational. So, as always, we want to begin exploring rational functions, their features, how to graph them, on and on and on. But before we do that, I just want to go back and review probably the most basic rational function there is, which is one that we've studied in the past. So let's just talk about some of the things we know about it, because they're going to relate to elements of more complex rational functions as we move forward. So let's just begin by graphing a few points. If x was 1, y would be 1, and if it was negative 1, y would be negative 1. If we had plus or minus 2, we'd have a half or negative a half. If we had a half, we'd have these values. So right away I've got a couple of points of accuracy. Now what I want to explore more carefully is what's happening at values around 0. So if I were to take values, we know that at x equals 0 the graph is undefined. But if we were to take values close to 0, getting closer and closer to 0, and watch what happens, just want to remind ourselves what happens when we have this situation. So if I have 1 divided by 0.5, that's 2. 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. And hopefully what you're noticing is that as we take values of x closer and closer to 0, our y values are getting larger and larger. And if we graph those, what we're getting is points higher and higher, closer and closer to the y-axis, which reminds us that a vertical asymptote is happening here. Okay? And similarly, we could take negative values for these x's and get negative values for these y's. We know that the asymptote extends down this way. And because the y-axis is a vertical asymptote, we dot that in just to show that. It's not part of the graph, it's just it just helps us graph, make an accurate graph. Right, so the one thing we're reminded about, just to summarize, is that as we take values of x closer and closer to 0 and divide the numerator by that, we get y values that are larger and larger. So we get a vertical asymptote, which is a typical feature of a rational function. Not every rational function, but many rational functions, as we're going to see. Alright, the other thing we want to talk about is what happens on the end behavior of the graph, out this way. If we take values of x which are large or very negative, what happens? So here we go. 1 divided by 10 is 0.1. 1 divided by 100 is 0.01. And if we keep doing that, we're reminded that as we take 1 and divide by larger and larger values, infinitely large, our y values get closer and closer to 0, which creates, as we remember, a horizontal asymptote on the x-axis. And similarly, we can take negative values and get corresponding negative values close to 0, and so it extends out this way. And so we're doing this to remind us that rational functions not only have vertical asymptotes, but sometimes horizontal asymptotes. So now that we've reviewed that, let's just go back and look at some more complex types of rational functions. And what I've done is I've graphed a number of these with a calculator. You'll see the first one here. I have a rational function, a more complex equation, and its graph above from the calculator. And I just want to talk a little bit right now about how the equation and the graph are connected and how we can figure certain things out. And then in future videos we'll work towards graphing rational functions on their own. Now, the one thing you're going to find about rational functions is that the graphs can vary quite a lot depending on the equation. There's not a predictable shape in many situations. You can get a lot of different looking types of rational functions. So in this first one of the things you typically want to think about with rational functions is, where is the denominator undefined? Well, here I have x squared plus 1, and I know that that can't be 0. And if I think about that, I'll realize that it doesn't matter what I pick for x. Any real number, my function is going to be defined. So it's going to be connected all the way along, which is what I'm seeing on the graph. There are no gaps or vertical asymptotes interrupting the flow of the graph. In terms of the range, well, I can see from just using the graph that my graph has a maximum value of 2 and down to negative 2. And so my range is between negative 2 and 2. All right. In terms of this course, finding the range will be done mostly by looking at the graph with our calculator. We're going to see that in our work in this unit, some things we'll be able to decide analytically by thinking about it. Other things we'll need to use the calculator to decide. The domain we can figure out on our own. The range we'll usually need the calculator. What about the x-intercepts? Well, the x-intercept, I can see on the graph that there's an x-intercept, 0 the function at 0, so x equals 0. Would I be able to determine that on my own from the equation? Well, if I look at my equation, I know that the x-intercept occurs when y is 0, and y would be 0 when the numerator is 0. In other words, when 4x is 0. So 4x is 0 when x is 0. So there's something I can figure out on my own without having to look at the graph. The equation of vertical asymptotes, well, I can see from the graph that there are none. And you'll remember that in the example I did with y equals 1 over x, the vertical asymptote related to the non-permissible values. And that in general is true. There were no non-permissible values for this graph, and so it makes sense that there would be no vertical asymptotes. And finally, in terms of horizontal asymptotes, it appears as though the graph is approaching something as it goes towards the end behavior of the graph, as we call it. What does the graph seem to be getting closer and closer to here? Now, if you trace that on your calculator, on and on and on, you would see that the y values were getting closer and closer to 0. And that's going to be how we determine horizontal asymptotes in this course, just by tracing and looking at what the graph is approaching, in this case y equals 0. Alright, let's look at another kind of rational function, one in which the graph looks completely different. Okay, and we have the equation. Now, just before we begin, this is a graph from a calculator again, and these lines that you see coming down here, they're not actually part of the graph. They're actually asymptotes, so which are invisible. They don't actually exist. Sometimes with the pixel structure of the calculator, you'll see those things show up. Other times you won't see it show up. But when you're graphing on paper, you should represent those as dotted lines. They're guidelines for graphing, but they're not actually part of the graph. So let's go through item by item to try to see what features of the function we can determine from the equation and which we need to look at the graph to determine. So domain, again, is the values of x that we can't use, and this relates to the non-permissible values, which in this case are plus or minus 3. And you'll notice that at plus or minus 3, we have vertical asymptotes, which remember means if we plug values of x close to plus or minus 3 into our equation, our denominator approaches 0, and our number on top, which would be close to 9 divided by something close to 0 would cause y values which are very large or very negative, thus creating the vertical asymptotes. Okay, so what we're saying is that the restricted values on the domain relate to, in this case, vertical asymptotes, which was what we saw when we looked at y equals 1 over x. The range we know is always more difficult to determine. We usually need to look at the graph for that, so I'm going to come back to that one. Let's look at 0 of the function, the x-intercepts. It looks like the graph hits the x-axis at 0, and as we said with the last example, the x-intercept is when y is 0, and y is 0 when the numerator is 0, and that would be when x equals 0. So that I can determine from the equation, and I can see it on the graph. In terms of range and horizontal asymptote, I'm going to look at horizontal asymptote next, and that means that I need to look at the end behavior of the graph. If we were to trace along here, further and further to the right, what value of y would the graph approach? And similarly to the left. Alright, so if you take your calculator and you trace along and you try to figure out what that is, you're going to see that the y values approach 1 on both sides. In other words, there's a horizontal asymptote to dot in right along there. And then in terms of range, which is all the y values being used, we can see from our picture and what we've determined in terms of asymptotes, horizontal asymptotes, that the range would be y is greater than 1 or 0 or less, including 0. Okay, here's another example of a rational function. Again, the graph looks quite different, and in this case it looks quite simple. So we have our polynomial divided by polynomial. We have a rational function in which x can't be 3, so that relates to the domain. And if x can't be 3, it means that when x is 3 here, there can be no point on the graph up here, if this was to continue on linearly. Alright, now, I can just see from the picture that the calculator's given me that it doesn't look like I have a vertical asymptote going on here. So what exactly is going on here? Well, one thing you might notice is that this particular rational function, you can factor the numerator as x minus 3, x plus 2, and the x minus 3 cancels out, and so we're getting our graph reducing to y equals x plus 2, which we know is the equation of a line, but the condition is that x can't be 3. And if x was 3 here, y would have been 5. And so this point, 3, 5, that you see here, actually is not part of the graph. And so there's a gap in the graph that we call a point of discontinuity. Sometimes we call it a hole in the graph. In other words, the graph is a line with a gap in it, a point of discontinuity. So at this non-permissible value, there's not a vertical asymptote happening. There's no vertical asymptote. What there is instead is a point of discontinuity at 3, 5. Typically on the calculator you won't see the gap unless your pixels, your window dimensions are set just in a certain way. But you need to be mindful of the fact that when there's a non-permissible value, in the past those have shown up as vertical asymptotes, but now we're seeing that they can also show up as gaps in the graph or holes. The next thing we'll jump to in our list of things is x-intercept. When y is 0, the numerator that's left is 0, so that would be negative 2, and I can see the graph crosses the x-axis at negative 2. And in terms of the range, well, now that we know that it's a line, we know that all y values are possible except 5. And in terms of end behavior, there are no horizontal asymptotes.